When I'm first working with students through research projects, the software TOPCAT comes up a lot. TOPCAT is called the tool for operations on catalogs and tables. The icon is a little yellow cartoon cat, which if you were in my generation, you know the cartoon that comes from, but today's generation of students might think that's very random. In any case, it's a very useful tool for astrophysics specifically, can be used in other disciplines, but it's got a lot of built-in astrophysical tools. Now, it's a program that's written in Java, so it should run on your operating system, no matter what your operating system is. And it's a little bit like older looking, the interface, I would say, but it works really well. It just takes a little bit of time to get used to. So I'm going to take you through an example of loading a couple of tables into TOPCAT, matching them up, giving a first look at the data and showing you how it can help you look through your data sets and understand your data better. So this is the kind of basic window of TOPCAT here, and it's just, it has a list of tables. We don't have any tables loaded at the moment, and it will put the properties of the table there. So the first thing we need to do is load a new table. Now there is a menu you can also use, but these are little shortcuts here at the top for various menu items. Not all the menu items have shortcuts. But most of them do. So if we want to load a new table, there's a couple of things you need to know. First of all, the format. Unless you're reading in a fits table, you need to specify the format, and there are multiple different formats here. The most likely ones you'll need are CSV, maybe VO table, but it's most likely to be either a fits table or a CSV. Now you can use the Java file store browser, but it's kind of ugly, so I prefer to use just the browser that my system is used to, and I have a Mac, so this is my normal file browser with the Mac. Now I've loaded a couple of catalogs in here. I'm gonna pick one, and here is an example of a rather large table. Now here are the table properties here. So this is the name of the table. This will just load in with the file name, but you can change the name here. Like it didn't load in the whole file name, so I could just be like, this is telling me all the different things that it's matched to, but it's actually like the Sloan Digital Sky Survey matched to many catalogs. Then I hit enter, and that new table name is kind of saved. It's just in this temporary session that's saved in, but that'll help me in this table list kind of keep track of as I build in more and more tables, this becomes more and more important. So it'll give you a couple of bits of information like where the file is, and how many rows it has. So this is how many, in this case, galaxies are in this table, how many columns it has, so how many pieces of information are available for each galaxy. This is a big table. This is 788 columns. That's huge, okay? I can sort the table by any of those columns that are able to be sorted. I don't need to do that right now. I can, once we get into subsets, we can show only subsets of those tables. And then there's this thing called activation actions. In fact, let me make this a little bigger so I don't have to scroll. This thing called activation actions, which I'll come to in a second. There's pretty much always one of these going to be loaded, but you don't need to worry about it for now. All right, so what does this table actually look like? How do I understand what my table has in it and then what the actual data is? So the first thing is you might be interested in like what we call the table schema. This is the column view here, so you can look at just what the columns are in the table. This doesn't show you the data of the table, but it tells you what are each of the tables named for a start, and if there is any description. So if anybody has added any additional information about what that column in the table actually does, that'll be here. And then there's these tick boxes, which let me show you what the tick boxes do. So if you don't want to look at just the table columns themselves, you can look at the table data itself. And that's that little button there. And that brings up the table browser, and that'll allow you to look at everything. So there are, 235,000 rows in this table, and I can scroll through the entire thing. Try doing that in Excel quickly, not easy. But also, so this is going to show all 788 columns as well, because all of those columns load ticked, all of them do. So if I come back here, I can actually use these various things. So these do different things. You can add a new column, and you generally will define that as from a previous column. You can add, you can like replace columns if you need to change the data a little bit, like I'll come to that in a bit. You can select certain columns like so, and then I can go, I only want to hide those columns, or I only want to show those columns like so. You can just have one click and untick them all, and you can see what it's doing here. This is showing you what the table is that you're actually viewing, right? So this is very handy. So you can be like, no, I want to tick them all, or no, I want to untick them all. And it's taking a minute because there's 788 to show or hide. But actually I could just be like, all right, what if I only want to show, okay, this is an object ID. This is from the data release 7 of the Sloan Digital Sky Survey. I know that because they all, well, it says DR7 in the column name, but they also all start with a 5, and that's kind of a signature of Sloan Digital Sky Survey old object IDs. I think they're now on data release 16, so these are kind of old, but that's okay. And this is the one used by the Galaxy Zoo 2 survey. Cool. And it says that right here in the table description. And then the RA and DEC, so the coordinates, I want to keep those. Now it also has the RA and DEC written a couple of different ways. For people who are observing, these can be a little bit easier, and there are various reasons people sometimes like to keep these in the kind of strings with the various formatting, but for now I'm just going to hide these because I don't think we really need them. And then I want to just have some example data showing, so I'm just going to go and do that pretty quickly. So total classifications, let's keep track of how many people voted for certain things. This is the question, does it have smooth, is it mostly a smooth galaxy, or does it have features? The first answer is that it has smooth, and there's a number of people who gave that. There's a fraction of people who gave that, which was later weighted by the user, so I'm going to put that on. I'm going to put on the total count and the weighted fraction for all 3 possible answers for this. Cool, and then I might be interested in one of the other questions, for example, if it has a spiral. Sure, let's do a spiral. Or if it doesn't have a spiral. I'm going to keep that, although these should always add to 1, the weighted fractions, because this is just a yes or no question. Fine. I'm going to scroll through the rest of Galaxy Zoo because there's a lot of questions. And then it now moves into some other information. So this is all information from the original Sloan Digital Sky Survey data release 7, and it has certain bits of information that we might find useful. So I'm not going to go through all these columns here, but when you're doing your full project, you might want to use these various columns. This is another catalog that was matched to, which is these letters stand for the 4 author last names of the paper. That's why it's called Aussie anyway. And so there's various information that is derived from the spectra of the galaxies in here. So these are things you might be interested in using if you're trying to, say, determine if a galaxy has an AGN, or if you want to know how star forming it is, that kind of thing. You can get that from the spectra. There's also the MPA-JHU catalog, which has further information. So all of these matches were basically already done. So I'm going to go ahead and tick up the redshift column here. So that should show up here. So this will give the redshifts of all the sources, which is measured from the spectra. I'm going to use the stellar mass here. These are uncertainties on the stellar mass, but I'm not going to have those for now. I'm going to use the star formation rate here, and that's SFR. Maybe I want the median actually instead of the average, but that's not a huge deal. There's a lot of documentation on this that I'm kind of glossing over right now. Another catalog, NYU Value Added Galactic Catalog from New York University. They did a bunch of other stuff here. I'm pretty much not going to use this for right now. And then WISE is a survey. This is the later data release 16, in case we were missing things, from which you can get updated magnitudes and colors. So the U-band, the G-band, the R-band, the I-band, and the Z-band might be useful to us. So now I've got this. I'm going to close this, by the way. So this thing generates lots of windows. TOPCAT generates lots of windows. The only window that you always have to keep open is this one right here. If you close this window, you're closing all of TOPCAT, but I can freely close any of the other windows, and it's no big deal. So this is the column schema, but everything is kept, so I can just reopen it as I need to, and it'll just remember where I was. So that's useful. It keeps your desktop from getting like too cluttered. All right. Now, okay, so I've got this table and I can start to explore via various tools. So I can do things like, what if I want to make a histogram? I don't necessarily need to write a big piece of code. To do that, I can just say, well, the object IDs is what it automatically populates, but that's not necessarily that useful. You notice this isn't showing me all 788 columns. That's because only 22 are apparent right now because I've hidden the others, and those are the only ones that show up in the list. So what if I just want to see what the redshift distribution is? Okay, So this looks like it's peaked at about redshift 0.08 or so, which tracks with what I know. I don't know what these things are. These are pretty high redshift objects for this particular survey. And so, all right, cool. Those are interesting outliers. I can also do other things here. Like I can change the bins. I can change the size of the bins, and it'll tell me, it'll make a kind of higher resolution histogram, but maybe a little more noisy. And of course, the smaller they get, the more noisy it gets. Or I can make a really chunky histogram here, so much so that it's sort of not useful anymore and so on. But it tries to guess when it starts what the binning size should be and so on. Okay, and then I can also do things like if I wanted, there's a lot of objects here. So what if I wanted to maybe make these logarithmic? That changes the shape a lot. It makes it's not a great thing to do for histograms. It makes it look kind of weird, but these are useful. And you can also do all kinds of other things with the axes. Like if I wanted to change this so that it doesn't have this label, which just happens to be the column name, I can make that say redshift, so a little bit more user-friendly. Now, I will say that when you're making plots with TOPCAT, you can get into this like specialization of things and changing the range so that it zooms in on what you want, and you can change the fonts, and you can do all this stuff, and you can make it look okay, but it still isn't really like report quality. You're still going to want to write code that generates your plots in, say, Python, because those are going to be more replicable. Like as soon as I close TOPCAT, this plot goes away, and I can save a plot here, but it doesn't really save it in a useful form. It's just not very replicable. And you can't like write a script to generate the plot with this, at least not easily. So you're better off like only using this as first look type of stuff, and you should feel free to make plots in the first look mode, but when you go to make your final plot, you should make it in Python. Okay, so what if instead I want to make a scatter plot? That's that kind of blank thing here, and if you hold your mouse over, it'll say just a normal plotting window. This is a scatter plot. You can plot in multiple dimensions if you want to, but I don't usually find these particularly useful. All right, so it's brought this up. It thinks I want to plot the first two columns against each other. That's just what it's guessing. That is not useful for me. What I might find useful is like, what if I wanted to look at like the G-band magnitude versus like the R-band magnitude here? Okay. The first thing I'd note is that obviously this is going to be just increasing numerical order, but that puts the faintest things at the top of the diagram, which is a little bit weird. So I might want to just flip both of these so that I can see this in kind of brighter things are on the top right. All right, and I can see here that the data is a little bit messy. That's the first takeaway that I get from this. There's kind of this sort of general locus here, and then there's like this whole series of things out here that are maybe a little weird. Like these are extremely faint. Like something went a little weird with this. They're really bright in the R band, but they're really faint in the G band, which is possible. They could just be like really, really red objects, but like okay, maybe they're weird. It's hard to tell. And then there's these lines, which whenever you see like a straight line like this, that always means it's like a selection effect or something has gone weird with the data. But like, how can we actually tell? Like, how can we go further with this? Well, this is where you can use the activation actions here. And the activation actions are really, really useful for certain things. So if I click the little activation actions shortcut up here, that's also in the menus. You can find that in the menus. There's a couple of things I can do. So there are other options you can add here. And in fact, if you're in the menus, you can add actions that aren't even included on this menu. They just didn't load them all, preload them all, but you can add others. So what I might like to do is display a cutout. And the cutout here is, all right, I'm going to tick it so that it does that. And then I'm going to say, sure, whatever, the RA and the deck, that's fine. Let me make this actually a little bit bigger so I can actually see everything. Field of view, 1 degree, pretty big, but we'll leave it there. We'll just leave all the defaults here for now. And I'll say invoke now on row 1, and it'll just tell me what that looks like. And this is what I see. So this has popped up on row 1 with my activation action, and I can click around and I can kind of see how this changes. So every time I click on these objects, it's fetching the coordinates from the table, and then it's using the coordinates in a search of a particular well-known place where you can search for things. For this survey, the Digital Sky Survey 2, and it is pulling a cutout, and it's showing me that cutout. It's 1 degree square, and it's rendering that 1 square degree into 300 pixels. Now, 1 square degree is big, and you can see what is the galaxy that I'm actually looking at here? I can't even see it. This is too small here. I can't see it. So actually, I might like to change the defaults a little bit here. So the first thing I might like to do, DSS is kind of an older survey, so I might actually like to look in the Sloan Digital Sky Survey because that's the data we're grabbing from. I'm going to use the color alt option just because I've found that I like that better. I can stand have a bigger cutout. I don't mind a bigger cutout. And I don't see the need to make it 1 degree. 1 arc minute would be fine, I think. Like 60 arc seconds, I think that's the same. So that would be absolutely fine with me. All right, so now I'm going to try to re-invoke that. And it's going to come up with a better cutout here. So there we go. So now I actually can see the galaxy that we are talking about in this particular row. And this is just in part of it's like the main part where most of the galaxies are. So cool. This is what the galaxies look like. They all have this range of, colors and, the 2 different magnitudes and fine. So, all right. The first thing is, let's look at these weird lines. What do we see here in these places where there's these weird lines? Oh, well, that's a sort of blended galaxy with a star, so I can see maybe the algorithm did something weird and just sort of was like, it's 25! It sort of guessed that it was 25 in this band because it couldn't see there's a bright star off here, and there's another bright thing here. Okay, let's keep looking there. And so if we're right that this is an issue when sources are blended and one thing is very bright and they're very different colors, it's just sort of setting it to some default value. Choosing 25, that this is all consistent. So maybe it does this in every band, that if it's got a problem in every band, if there's something bright nearby that's sort of messing things up, it just defaults to a particular value. Okay, so really we would want to probably clean this data out because we can't trust the photometry in these bands if we were going to be looking at that. Let's look over here, see what these objects are that are like red. Well, nothing, there's a bright thing there for sure, but I guess it's just sort of, that whole calibration looks a little bit weird. In the Sloan images, they are GRI color, so the R band is green. So maybe the green was a little messed up here because it had really high backgrounds. But it's not like soup, that's just a galaxy. Like, it's not really obvious anything's weird here. Maybe these are just really extra red. Okay, bright star. So maybe there's a combination of weird artifacts here and then also some just like very red things. I don't know. But it's actually it's actually true that as we're looking at this, maybe the looking at the 2 magnitudes against each other isn't the most ideal thing. If what we're interested in is looking at like different colors, for example, maybe we want to look at it a little bit differently. So I might want to make a color mass diagram. So I'm going to show you another thing you can do with TOPCAT, which is you don't have to stick in TOPCAT to just plotting one column versus another column. You can do things like arithmetic and so on. And so I can make what's called a color mass diagram here. Wow, why are these negative? That's a little bit weird, but all right. Oh, I know why they're negative. Because I was flipping. Okay, so something has clearly gone weird. There's clearly like a negative. So when the mass gets negative here, you see how these are auto-ranging. When the mass gets negative here, this one data point or this collection of data points where clearly nothing was actually found is like really, really messing with us. So I want to see, first of all, I'm going to look at the table itself and I want to see, okay, the median mass is given sort of in these numbers, and this tells me that this is in log. So it's in, this is going to be 10 to the 9.384803 is the actual stellar mass in solar masses of this galaxy, for example, or 10 to the 8.46423, whatever. So it's already in log, so taking the log isn't going to help me learn anything about it. So all I need to do here is, well, for example, I could take a subset. So this is this thing that looks like a Dr. Seuss fried egg. It's actually meant to be a Venn diagram, and then one circle's all inside the other. That's how they made a subset. Anyway, it's just what it's called. So there's already a subset that exists, and it's because one of the columns in here was actually like a tick box column, and we could see it if we showed all the columns, and it loads those true-false Boolean columns as subsets, but we can create our own. So actually what we might want to do is call this like has mass. You can put spaces in here, but it might make your life more complicated later if you want to use the subset or anything else. So I like to make names without spaces and without weird symbols and stuff. So we just want something that has like a, actual rational value for the stellar mass. You can't have a negative stellar mass. What does that even mean? So I'm just going to say MPAJHU the column name, median mass, has to be greater than 0. And that is my entire subset, my whole thing. Okay, so now the plot has changed, and I don't know if you can see this. Let me actually change this a little bit so that you can see the points a little more clearly. I'm going to change the size of the points. So you can see that it's defined the subset and it's added it to the plot. It just did that sort of helpfully. I can go in here to subsets and be like, actually, I don't want to see all. I only want to see the ones that have mass. And then I could either go into the axis thing here to the range, and I could specify a minimum and a maximum mass, or a minimum and a maximum color, which I might want to do later because these colors are bananas, but come to that in a second. I could also just have it rescale, and that's a lot better, right? So now I'm looking at only the things that have mass, but the colors are still really messed up. And so I could define a subset as well. But instead what I'm going to do for now is I'm just going to say, look, I know the colors should be ranging from like, let's say -2 to 2 or so. And I hit enter, and that was a little bit off. So it's actually more like -1 to 3. Great. I'm actually maybe going to make these points a little bit smaller. And actually what I'd like to do is maybe not make them so huge. And I might also like to make them something like this, so that I can see more clearly what where the concentration of points is. And you can still see that there are outliers, but like you're really seeing most of the points are like in these two kind of areas. Okay. That's just one particular way to do this. And this is very similar to in Python changing the alpha value on your plot. But it just helps you see the data a little bit better. So, okay, cool. I've got colors, I've got masses. I would like to see what these look like. So I'm going to maybe click around here. I'm going to maybe close the subsets window because I don't need it anymore. I haven't used it. I also don't really need the activation actions window anymore either. I can always bring this back up, so I'm going to close it. And that just cleans up my desktop a little bit. So I'm just going to click around, and in this area where the colors are more negative, which are bluer, what am I seeing? I'm seeing a lot of disk galaxies. And then in this area up here, I'm starting to see a lot more elliptical galaxies, and this is what I expect. Redder galaxies tend to be elliptical galaxies, and bluer galaxies tend to be spiral galaxies. But I don't have on this particular plot any information about it. What I might like to do instead is I do have information in the catalog because these are matched to Galaxy Zoo. So instead of using transparent here, what I might find more useful is adding an auxiliary axis. And that is to say, we're going to make the points change color based on some other quantity that you already have in your table. And one of the things I already have in my table is like, is it a disk or not? Or is it a smooth galaxy? Is it mostly an elliptical galaxy or not? That shows it a little bit better. So the things that have really high kind of smooth fractions tend to be up here. And the things that have a lower smooth fraction, so they're not mostly just smooth distributions of light, they tend to be down in the bluer area here. But it's not like a really obvious, I mean, it's definitely there as a correlation, but it's not like, it's pretty messy, right? So, okay, that's cool. All right, so that's kind of what you can do with a single table. And it's very powerful. And this thing where you can particularly be like, this galaxy is very obvious. This is like some kind of elliptical galaxy that looks a little blue and it's got some interesting things. Whereas this I can see if I click on the big yellow one, it's going to be, oh, I clicked on the wrong point. It's going to be a spiral galaxy, right? Now that it's ruining yeah, okay. So it's going to have some kind of features of some sort. Cool. But I might like to look at something else. I might like to bring in some other table. That this table that I have loaded, I already did a lot of work in TOPCAT to match multiple tables together. I matched about 4 or 5 tables together in TOPCAT to make this mega table, right? And then I saved it. And you can always save your table, but keep in mind, if I were to save this table right now, which I could do, I could save it as a fits table. I could save it in a new directory and a new name and stuff. It would only have these 22 columns showing. And if I wanted to, for example, only have the things that had mass, I could save, that's it cuts out about 3,000 galaxies that they didn't have a measured mass for. I could then save that, and it would have then the new table would only have these properties that were saved. Okay, but what if instead I have a table that I would like to match to? I happen to know that it's a CSV, so I'm going to pull that up and come back to the directory that I was in before, and that is this. So this is an additional table that has some further information on the spiral properties of some of these galaxies. All right, so what does this look like? Again, I'm going to look at the various columns. There's not that many columns in this one, so it does have the object ID, which might be the same as the object ID in this table, but I'm not sure. It's always safe to match on coordinates. Well, relatively safe. It has a couple of pieces of information. There's no real descriptions here. I got this from a colleague of mine who led a paper where they did this work, and I'm an author of the paper, so that's how I have the table. I'm happy to share it with you guys. So this is from Galaxy Zoo. This is the probability that the galaxy has a bar feature. That's also in the main Galaxy Zoo table, but these two things are not in the main Galaxy Zoo table. The M star, the stellar mass, also is, so that's just like additional information. But these two are different. So I know that this is going to be the like windedness parameter of the spiral arms, and it's as measured sort of using Galaxy Zoo. It's a long story. I don't want to go into the details. Anyway, this is an important column is the point. So what I might like to do is I want to know all the information for the galaxies that have it. Only 6,222 galaxies have these measurements, so it's certainly a lot less than this table, which is 230,000 or so. But for these 6,000, I would like to also be able to plot the spiral windedness or look at that information. And this is just one example. You could be looking at their measurements with an X-ray telescope, or whether they have radio jets or various things, right? So in order to do that matching, I'm going to use this match. It's two matches, so it's a pair match. That's what this icon is. If you go up into the joins menu, there's actually many different kinds of joins you can do. And you can match like 3 tables at once, 4 tables at once, that kind of thing. You can match on different things. So if I thought that the exact Sloan object ID was the right column to use, like if I thought those object IDs would match, then I could put that in here. I don't know if they're the right. I haven't tried it. Let's see. So I'm going to match on these two things. I'm going to say I want the best match in each case. And I could say I just want for every row in table 1, give me the best match, or for every row in table 2, give me the best match. In this case, I only want it to return the things where there was a match, but I could have it, for example, give me a thing with like 230,000 rows, but only filled in where the ones there are matched. And so you can make different choices here. But I'm going to choose this. Let's see if it matches. I don't know that these ideas are going to match. Oh, they actually do okay. 6,084 have the same ID, but the IDs in Sloan, it's a long story, but the IDs can change over time. So I'm actually going to delete this table. And I want to maybe try again. So if I delete this table, that's fine. It goes away. I can't get it up again. But I can do the match again. So I can bring this up and, okay, 1 arc second, it's a little bit, that is a perfect match. And that, if I were using different surveys and they had different calibrations to their astrometry, I might be off by a few arc seconds, but it's still a good match. So I'm going to make it 5 arc seconds as a radius. So since I've said that it's going to match on sky coordinates, it's going to try to find what the columns are that are already in deck. And so this is why you should name your column something descriptive. I'm going to keep it as best match in 1 and 2 and see what we get. And that found, same amount, see? So actually the IDs were fine. So we can use that. And now I'm going to close this window because I don't think I need it anymore. I can always bring it back up. And I am just going to call this SDSH, this is my kind of mega match. And then, spiral winding angles. All right, now that I've hit enter, that will save it because this match 1, 2 is not a extremely useful. It does tell you that it's a match between tables 1 and tables 2, but it's not a very descriptive thing. So I like to rename them where possible. Okay, and then I can also show you, for example, another way that we can do. So let's say I wanted to just sort by this. So the first thing is I just sorted the table. It didn't really change the plot at all. But I can actually go to where the plot is made, and I can say, well, can I remake this plot but with the new table, for example? Yes, I can. And look, it's already kind of nice and clean, actually. The colors are much better. It took out this entire bit up here. Oops, no, I've got to... I've got to do the HasMass subset and everything, so it's not going to be easy to switch back and forth between these. But it took out pretty much that entire upper bit there, where it had, what did I do? I did minimum -3 and up to 1, I think. Nope, I did it wrong. 3 and up to down to -1, yeah. So if we keep these the same, so if I just make this a 6 to, what does that look like, about 13, like so. And so if I make these the same and then I try to switch back, you can watch how this actually changes quite a bit. And we had this whole upper bit here, which was super red things, and that's just sort of gone now. It's just not there anymore. So this is really telling me that however this second table was made, and I would need to go back and read the paper where they talk about this table and how they selected the sample, because they selected against a whole bunch of galaxies here, and I'm going to need to understand that in order to be able to understand how that selection might have affected my science that I want to do, for example. Okay, so now this activation action is only for table 1, so it's not going to be useful for this, so I have to redefine the activation action, but that's easy enough to do here. Just come down here. Yep. Oh, there's RA1 and Dec 1. That wasn't what our original tables were. Actually, I want to show you that in a second, but before I get there, I want to change this to field of view, 1 arc minute. Pixel size, it doesn't really matter hugely. We could do 500, we could do 600. But really the thing that matters is that I choose this. Sloan color alt. Sorry, that got cut off there. Okay, so now this is now activated, and I can continue to click around here, and it'll just now generate a new thing. And it generates this new window, which is, I still have the other one up, and I can still change things in table 1, and it will show me what those look like. But now we're showing what we're looking like in table 4 now, because I deleted a table and it remembers that. But I don't need to be using a plot to look through my data. So if I bring up here again these the table itself, and note now I have sorted the table by this psi Galaxy Zoo 2 value, and it looks like it's sorted increasing, or I could change it and I could sort it decreasing, and it would start with the highest values. And I've just sorted the table this way for my own convenience. Again, if I saved the table right now, it would save that way. But this is telling me, like, what is this parameter measuring? So if I start here and I'm looking through the various galaxies here, it looks like this is kind of looking through like loosely wound spiral arms. That pretty much looks like what this is looking for. So these are quite kind of loosely, and some of these, this looks almost more like a tidal tail than a spiral. This is so loosely wound. Whereas if I scroll through down, go down here, these ought to be more tightly wound spirals. Yeah, and they are. With this, that's a nice one. Sorry. So with this, I can look at this to, first of all, try to understand what's actually in my data, what's it measuring. If I want to look at this and just remind myself which direction psi goes, is a higher number a more loosely wound or more tightly wound, I can look in the data and verify that. I can also look at, like, is the data any good? Is the measurement any good? Like, how contaminated is the data? Like, if I'm scrolling through here, at what point would I say that this stops being a tightly wound set of spiral arms? I could just keep scrolling through this data and keep looking at that. At what point would I say that? And what point would I change the kind of classification if I had to put them into buckets? For example, this is really powerful, this ability to look at images. I do want to point out that there is another type of activation action. It's not actually in the default menus, but you can, it's just called display image. You can get to it from the main TOPCAT menu. And it's just called display image, and it requires something that we don't actually have right here in these tables. I will try to find a table that has it in a minute, but it has the ability to, if you have a column in your table that has either a file path on your own machine, like C:/, that tells you where the image is for that galaxy, it can pull that up and show that to you instead of having to fetch a cutout every time. Or if you have a URL that you want it to fetch and show you, so it doesn't have to show you an image on the sky. It could show you a plot, right? You could make plots for each galaxy, and it could bring up the plot for every galaxy, and you just have to tell it where to find that, and that will have to be a column in the table. And what this is going to do, it doesn't have any columns because there's no columns in this table that are formatted as a string, so it knows there can't be any way to do that. But I have added that as a menu option. Let me just add another table here just really quickly. Let's see, let's sort this here. I hadn't really planned to do this, but I'm going to do it anyway. I know I have this in a couple of places, so let's do this. Galaxy Zoo, Hubble. Oh, it's because I said it was a CSV. By the way, if you get this error, I didn't notice that I had my table format as a CSV, but it's actually a FITS table, so I got a data error, but that's fine. So that just means I have to just come back up here, and auto works fine with FITS, but it's fine. I can specify that it's FITS, and then I just reopen it. It'll be fine. Okay, so now there's 100,000 in Galaxy Zoo Hubble, and there's 262 columns, et cetera, et cetera. But the main thing is there are some string columns here, and there is particularly an image URL. So I don't have to use the RA index. I can use the URL itself, and it's already given as a column. So I can use display image here instead of display image region or display cutout, and it's looking for any column that has strings in it, and it is in fact the image URL. And I can just say, okay, now bring that up, and it's going to bring that up and pull the URL, and this is what this image looks like. So now, instead of looking through some cutout service, these are Hubble images that are color images, and it has made these, the project has made these separately, so I can just access what the project has already made in this particular way. But again, this doesn't have to be a URL to a website. This can be a path to a file on your own computer, and that works fine too. It just has to be a full file path. So if you are on, you have to start it with, instead of http:// you have to start it with file://. Like, for example, if you're on a Mac, you have to do that. But if you're on Windows, try it out with that, or try it out with just C drive and so on, what your normal file path would be. Anyway, so now we have a lot of windows open. And then, so the last thing that I think I forgot to show you earlier is here in the matched table, there's two things. The first is that there were both the tables had columns named RA and DEC. And so it had to resolve this conflict somehow, and its default for how it does that is to just label the first ones RA1 and DEC1, and the second one's RA2 and DEC2. You can always just edit the table thing. That's absolutely fine. And then if I wanted, I could save this. So I'm going to close this. I could save this table somewhere. I could save it as a FITS table, or I could save it as a CSV. So this is actually, TOPCAT is actually really useful for converting. If you have a FITS table and you just wanted a CSV, just open it in TOPCAT and save it. You can do that in Python as well, but if you wanted to save it into a weird format, you can always do that. So for example, if I wanted to save this as GZ2 mega match with spiral angle dot, I said CSV. Did I say CSV? Whatever. Anyway, so now I've saved that table, and that is saved, but it's while I'm working with it here, nothing is saved. Okay. So one last thing that I want to show you, before you you take off and start working on TOPCAT, is saving a session. So if you want to just basically, like, if you need to shut down your computer or something and you want to save your work, and you want to be able to come back to where you were with your session, with your whole session, you can save your entire TOPCAT session here, and you can pick which tables to save, and then it saves it as this thing called Fits Plus, whatever, and you can save GZ2 demo. This is actually Sloan. I don't know why I called it that. It's the Sloan Digital Sky Survey demo session, and this is definitely, you want to save this as a Fits. Anyway, so then you hit save. It takes a minute, especially because I have a really big table here. But what I'm going to do is I'm going to close TOPCAT here for a second, close it out completely, and start it back up. And then you can see what gets saved and what doesn't necessarily get saved. Like, it doesn't always do the best job of saving subsets and things like that. So now I've shut down TOPCAT. I don't even know, whatever. So I'm going to open it again. It's going to take a second to come up. Cool. Now, let me bring this back up. Now this is empty. It remembers absolutely nothing. And then I am going to open this from the session. I'm going to leave it on auto because it can handle that. I'm going to open SDSS demo session, and it recognizes it's a Fits Plus. There's multiple tables, and it just brings up what I had before. Now, here's the question. Did it remember things like my subsets? Yes, it did. It did a good job with that. Good. I will say that when you save your work, this is a good way to save your work in TOPCAT, but it doesn't always save the way you think it is. Like, I have occasionally brought up a session that I saved and like the subsets didn't save, or the table names didn't save, and it's just like table 1, table 2, and you're like, oh my God, because you keep a lot of information in this. So my suggestion is that you basically save like an A version and a B version, and every time you overwrite your work in progress, that you just save the A version, and then last time you saved A, so now you save B, and so on, so that if something like that happens and you do have like a catastrophic issue with the saving, it won't necessarily tell you that it's had a problem. You're only like one version behind. But like I said, don't get too dependent on TOPCAT, okay? Once you figure out kind of what your data looks like and that you can make this color mass plot, like I wouldn't want to save that color mass plot and then put that in a report. It's not report ready. You need to do a lot more work. You need to understand how to clean your data, apply that data cleaning. You can practice with it in the subsets. You can be like, I want to clean it by only showing the masses above 0. But what that actually means is that when you're writing your report, when you're doing your analysis, you need to put a line in the Python script that when you read in your data, you need to add the data cleaning and set a subset that only has, the masses are greater than 0, etc. And so this is a tool to help you be more efficient with how you're interrogating the data, but it isn't the only tool that you use. However, it is quite powerful, so do go forth and make plots, make tables, and match everything up.